Welcome to Lecture 4 or Advanced Geospatial AI, Deep Learning for Satellite Imagery Analysis. I am Dr. Azad Rasool, and today we are introducing deep learning for geospatial tasks using CNNs. We will use real Sentinel-2 Level-2A data from Google Earth Engine to classify land cover forest versus urban in 1 by 1 kilometer region in Brazil. You will build a simple CNN in Google Colab and preview an advanced ResNet 18 model. Let's dive in. What's deep learning? Deep learning uses neural networks with multiple layers to learn complex patterns from data like Sentinel-2 imagery. Unlike traditional machine learning, deep learning automatically extracts features, making it ideal for high-dimensional satellite data. CNNs excel is geospatial tasks because they detect spatial patterns, like vegetation or urban structures, in multispectral bands. Today, we'll start with a simple CNN and preview a ResNet 80 model to see how deep learning scales. Here is why CNNs are perfect for satellite imagery. First, spatial feature extraction. CNNs identify patterns like forest edges or urban grids, critical for land cover tasks. Second, multispectral support. Sentinel-2's Level 2A bands, for example, RGB and NIR, are processed as input channels, enabling tasks like NDVI analysis. Third, scalability. Collapse GPU acceleration handles large datasets from GE, as in our project. GE Authentication and satellite datasets. To access Sentinel-2 data, we use Google Earth Engine with a project ID. My project is 399-218. GE requires authentication, which we will cover in the demo. Students need a GE account linked to a Google Cloud project. If my project is restricted, create your own project. Beyond Sentinel-2, other datasets enhance geospatial tasks. For example, Landsat 8 and 9, 3 meter resolution, ideal for long-term land cover monitoring. MODIS, daily global coverage, for large-scale environmental analysis. PlanetScope, 3 to 5 meter resolution for high-detail urban mapping. Eurosat, pre-level Sentinel-2 dataset for benchmarking. These datasets accessible via GEE. Coding the most simple CNN with a Sentinel-2 data. Let's build a simple CNN in Google Colab to classify land cover using real Sentinel-2 Level-2A data from GE. Open the Jupyter Notebook from the course resources. Enable GPU and follow along. You will retrieve a 1 by 1 kilometer region in Brazil. Process it into 10 patches, RGB plus NIR, and train a CNN with the simulated levels for this introductory demo. It's our script. Install required libraries. Pip install Torch Vision, Scikit-Learn, Earth Engine API, and GMAP. These libraries, PyTorch for deep learning, Scikit-Learn for metrics, and GMAP for GE are pre-installed in Colab. We comment out the pip install to save time. We use PyTorch for building the CNN, Scikit-Learn for accuracy, and GMAP to access Sentinel-2 data via Google Earth Engine. Then import libraries. We import libraries for deep learning, Torch, NNN, and Optim. Data processing, NumPy, across calculation cycle learn, and GE data sys, EE, and GE map. These libraries handle deep learning, data processing, and GE integration, enabling us to work with a Sentinel-2 imagery for land cover classification. Authentication and initialize GE with a project ID. We initialize GE with a project ID. My project is 399218. To access Sentinel-2 data, the try except block handles authentication errors, copy the token from the browser and rerun this cell. Set random seed for reproducibility. Torch.manual seed 42. We set a random seed to ensure our results are reproducible, a key practice for debugging deep learning models, and compare model performance in this introductory demo. Define region of interest. We define a 1 by 1 kilometer region in the geography for data analysis suitable for forest versus urban classification. Then retrieve real Sentinel-2 Level-2A data, atmospherically correct, for GE Cloud 3 2023. The name of product, filter bound to ROI, filter date, filter cloud, less than 10%, dot first. We fetch a Cloud 3 Sentinel-2 Level-2A image from June 2023, filtered by our date and low cloud cover, ensuring high quality data for CNN input. Select RGB plus NIR bands. We select red band 4, green band 3, blue band 2, and infrared band 8 for key for land cover classification. NIR supports vegetation analysis, for example, NDVI. Export to NumPy array and process into patches. Normalize reflectance. Crop into 32 by 32 patches. Limit to 10 patches for demo. We convert the gene image to an NumPy array. Transpose to channels height and width for PyTorch. Normalize reflectance from 0 to 10,000 to 0, 1 and split into 32 by 32 patches. We limit to 10 patches for this demo. Output 10 for 32, 32. For demo, for example, or forest, one urban, you can use real levels in your assignment or real research. Real levels, for example, WorldCover will be used in assignments to improve accuracy. Custom dataset class Sentinel-2 dataset. This custom dataset class prepares patches and levels for PyTorch, converting them to tensors for efficient training. Dataset. Dataset equals Sentinel-2 dataset, patches and levels. Data loader, dataset, patch size 5, and shuffle equal true. We write our dataset into a data loader, which batches the data and shuffles it for training, optimizing GPU performance. We create a dataset from our 10 batches and load it into a data loader with a batch size 5 and shuffling for randomized training. Define a simple CNN model, input bands for class 2. We define a simple CNN with one convolutional layer, 4 input bands to 16 filters, rel activation, max pooling, and a linear layer for 2 class, forest and urban. Then initialize model, loss and optimizer. Use coda if torch.coda is available, else use CPU. Use optim.adam model for optimization. We set the model to run at GPU if available. Use cross entropy loss for classification and Adam optimizer with a learning rate of 0.01 for training. Train for 40 epochs. We train the model for 40 epochs, processing bytes, computing loss, and updating weights. Then evaluate and train accuracy. We evaluate on the training set, no validation split. Let's manage runtime. We select T4 GPU, then run. Executing. Hello. Continue. Continue. Patch shape. 10 for 32, 32. Accuracy 4.90. We evaluate on the training set, no validation split, achieving 4.90 accuracy. This unreliable due to the overfitting and lack of a separate validation set because we are training set with only 10 patches causing overfitting. This demo introduces CNN basics but highlights the need for larger datasets and real levels for achieving, for example, near 0.95 accuracy.